Okay, then welcome to the third chapter of mobile communications. Now we go from the physical layer to layer 2 and look especially on the medium access. We'll focus on the differences between medium access and fixed networks and now those wireless systems. And you will see how closely this layer interacts with the physical layer, because now we use, for example, the multiplexing technologies like space division multiplexing, frequency, time, and code division multiplexing for space division multiplexes. So that means we use multiplexing plus a clever algorithm results in a multiple access technology, because the algorithm has to say when to use the resource. We will look into some different medium access technologies, start with a simple LOA system and look into some collision avoidance schemes, and we'll compare them. Not complicated, just to show you the differences to the fixed networks. First of all, why do we have to talk about medium access? I talked about medium access already in telematics. Several lectures I showed you medium access technologies. And in the end, I always said, oh, it's so boring because we have star topology and full duplex wires. Boring because there's no collision anymore. We have a switch in the middle controlling the medium, so nothing can really happen. So we don't really need special medium access algorithms or whatever for fixed networks. It's very simple. And for the worldwide backbones, we have point-to-point connections anyway. So there's no collision in point-to-point connections. Also not interesting. But you might remember there was something called CSMA-CD. Yes, that was a technology developed for media that might have collisions. CSMA-CD, that was carrier sensing, so listening to the medium. That means listen before you talk. So carrier sensing, multiple access scheme with collision detection, so listen while talking. So that means you listen to the medium while you send something. So the idea is you send as soon as you see the medium is free, and you listen into the medium if there's a collision. That was the legacy method in IEEE 802.3, the classical Ethernet. So now the problem is, if we have a wire, that's nice. So we have a wire, and we have someone limiting the length of the wire. That's a standard. The standard, it says maximum 200 meters. Okay, then you know, okay, the technology will only work with the maximum length of the wire of 200 meters. How do you do this in wireless systems? To spray a white line at Kurfürstendamm and say, okay, you must not step over this white line because then you drop out of the cell? Doesn't work. Electromagnetic waves suddenly stopping after 200 meters doesn't work. Here, for our classical coax cable, we had a resistor, and this resistor actually, well, swallowed the whole signal. There was no signal reflection, and that's it. Okay, we don't have this for electromagnetic waves. We cannot stop them. So the problem is, well, our signal strength decreases proportional to at least the square of the distance. We know this. In vacuum, in space, in real systems, d to the power of 3.54, whatever. Something similar happens on the wire, but before this is really a problem, we limit the length of the wire. We cannot limit the distance to the base station. It doesn't work. So, that's the first problem. Okay. Second problem, only the sender applies carrier sensing and collision detection. The problem is collisions happen at the receiver, not at the sender. So if two stations send something, imagine we have a huge mountain, the base station up here, and you have a mobile phone here and a mobile phone there. They perform carrier sensing. Oh, the carrier is free, medium is free. They both send. We have a collision here at the receiver, not at the sender. So sender applies carrier sensing, free medium, great. Sender applies collision detection, great, no collision. Why? Because the collision happens up here. The collision is too weak to travel back depending on the signal and on this constellation. So it might be the case that the sender cannot hear the collision. CD doesn't work. The CS might not work if the terminal is hidden. That's exactly the scenario here. Why don't we have the problem here? Because also on the wire, we might have similar scenario. We have a receiver, and we have a sender here and a sender here. Now we apply carrier sensing, medium is free, we send. It could be the case, that's what I explained to you for the CSMA CD technology, that we send more or less at the same time. Then also we have a collision. But if we have a cable, this collision spreads out over the cable. And the cable is short enough that all participants in the cable will hear the collision. And then they send the jamming signal. In wireless, we don't know if we really receive this. So that is the problem, that the collisions occur at the receiver. But the senders, they apply the carrier sensing and the collision detection if we use CSMA-CD. And this is why CSMA-CD simply fails in wireless networks. But yes, you can use it and maybe it works sometimes, so carrier sensing is always a good idea, but it's not enough. That's the problem. So carrier sensing, well, it's okay, but as you see, it's not enough. So it might simply not work if a terminal is hidden. So, and that's exactly one of the key problems we have in wireless systems, so-called hidden terminals. A hidden terminal, here, simplified example, we have 3 terminals, A, B, and C, and we have the transmission ranges shown here in blue, red, and green. If you draw this also in the exam, please draw it in a way that the transmission ranges really covers the other terminal, because otherwise it will not receive anything. But as you see, the green signal, let's call the green signal, will be too weak. It will never reach A. And because there might be some interference, but not transmission range, as you see. Okay, now if we assume A sends to B, C cannot receive A. Or vice versa, if C sends to B, A cannot receive C. So, if C or the other wants to send now, it senses, if we use carrier sensing, and says, great, free medium. That means carrier sensing fails because the medium is not free. At the receiver, it's not free, and that's what is important, not at the sender. So we have a collision at B, and CD fails because we cannot receive the collision. And this is why we say A is hidden for C. In this case also C is hidden for A. So this is called a hidden terminal. And the hidden terminal problem is really a problem in wireless communication. We can make things even worse. We can now say, okay, B sends to A. Other scenario, B sends now to A. C wants to send to whatever, some D, somewhere. To whatever. And now, due to this constellation, C has to wait, because if you apply carrier sensing, the medium is in use. Because, as you see here, C receives the signal of B. But as A is completely outside the radio range of C, waiting is not necessary. C could send at the same time as B is sending, because A will never receive the signal of C. It doesn't matter if there is some interference at B. The green signal will never reach A, never. So, okay, A is outside the radio range, waiting is not necessary. This is why it's called C is exposed to B. C is exposed to B, C cannot send, it performs carrier sensing, it cannot send, although it could send. This limits our data rate, because then the terminals wait, although waiting is not necessary. So hidden and exposed terminals, that's really a big problem in wireless systems, and they do not happen in wired systems because we limit the length of the cable. Without the length limitations, we'd have exactly the same problem, but typically we have these limitations. Okay, so that's one of the problems, hidden exposed terminals, and next time I will show you some other problems. and then explain briefly the classical medium access technologies we use in wireless systems, and then a little bit more about the code division multiple access, how we generate the code, and how to understand this. Because I'm pretty sure that up to now it's not really clear what does it mean, code division, and why these codes, and how does it work. Okay, thanks a lot for today, and see you next week. So, good morning everybody, and welcome back to mobile communications. The last lecture I start with the question of medium access. So why can't we simply use the medium access technologies we know from fixed networks? So I also told you all in telematics, oh, it's so boring with switched Ethernet, star topology, but we remember CSMA CD, the classical Ethernet. I showed you carrier sensing doesn't work. The main reason is collisions happen on the receiver side, not necessarily with the sender is. So if you try to do something like carrier sensing, like collision detection, it fails. So this brought us to the problem of hidden and exposed terminals. But in addition, we have some more problems. The next problem is called near and far terminals. Think of the situation where you have one mobile phone pretty close to, for example, a base station, and the other one further away. So the problem is that all the mobile phones, they have a maximum output power, let's say 1 watt or quarter watt or whatever. And you know you need a certain amount of energy to transmit your data. So what is quite clear, if you have a certain noise level, then it's much easier for a device that is closer to a base station to transmit something. That's similar to you sitting in the first rows. It's easier to talk to me compared to those sitting back there in the last row, if there's a certain noise level, which we usually always have in our environment, noise due to interference, etc., etc. If there was no noise, okay, that's an ideal world, but okay, we live in a real world. So what happens, it could be the case, for example, if the B and A, both they compete for sending rights, for example, and they say, oh, I want to send something, for example. Okay, then the signal from B would simply drown out terminal A, already on the physical layer, because the signal is much, much stronger. And C will obviously receive B, and maybe then there's some background noise, I don't know. So that's it. So we need precise power control, especially as you will see in CDMA networks that apply code multiplexing for multiplexing different channels. If you apply strict time division multiplexing, for example, then it's no problem, because then more or less you say, okay, now it's B's turn, then it's A's turn, then it's B, A, etc. No problem at all. But if you start sending at the same time and same frequency, and the only difference is a code, as I will explain today, then we exactly have these problems. So we need precise power control. Otherwise, well, the noise generated by B, when C tries to look into a signal, is just too much. So you will not receive anything. So CDMA does exactly this precise power control, and the idea is that, okay, the closer you are with respect to a base station, the less power you need. So, for example, B would send just with a quarter watt and A with 1 watt, and then, that's the idea, the signals have more or less the same strength when they reach C. And then C can apply the CDM, code division multiplexing algorithms, as I will explain, and then filter out A signal or B signal. So if all your voices have more or less the same strength, the same amplitude when they reach me, then I might be able to filter out, depending on the code you apply. Code, I will explain what this means, for example, for humans. So, precise power control, and for UMTS, this means 1,500 times per second, which is quite a lot. So you adapt the power all the time, what you said. Because this depends on the noise and depends on what does actually the base station see, what different kinds of signals, and then the base station will tell you, please increase or decrease your output power. That's the basic idea. Okay, that's the next problem, near and far terminals. So, this all shows we cannot simply use a classical medium access scheme, or we can use it, but maybe the performance is not as good. So now what we do is, we take our multiplexing schemes, space, time, frequency, and code, as you will see, and apply in addition an algorithm. So in the end, we use multiplexing plus an algorithm. This leads to multiple access methods. So, for example, space division multiple access. Well, the multiplexing scheme is space division, so we need guard spaces between antennas. Where's the algorithm? Well, for example, the Bundesnetzagentur will tell you where you are allowed to place a base station. And the network operators will think of, okay, this is my cell structure, I have a base station here, base station there, and we need certain guard spaces, or radio and TV stations, so they do cell planning, so that's the algorithm there, for example, for space division multiple access. Or if you think a beamforming, I showed you this MIMO technology with many antennas where you can do beamforming. This is where we can follow, for example, single pedestrians with their mobile phones. This is where we also can apply space division multiple access using space division multiplexing plus an algorithm. The same with FDMA, frequency division multiple access. So someone has to assign certain frequencies to senders and receivers. This might be, again, Bundesnetzagentur, for example. So administration that says, okay, this radio station is allowed to send on this frequency. Or it might be your Bluetooth device deciding, oh, I will jump through the channels using this and that pattern, for example. Okay, so we have different algorithms, different schemes for, in the end, well, distributing frequencies or time, TDMA, time division multiple access. So we have a fixed frequency, but then we can apply certain algorithms, round robin, for example, polling strategies, or very strict time multiplexing, as you will see, for example, in GSM networks. They say, okay, we have 8 fixed time slots, and then this is this conversation, that conversation, this conversation, etc., 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 and then it starts over again with 8 fixed time slots. So, multiplexing plus a nice algorithm leads to the access methods. Okay, so examples. For example, we can use frequency division multiplexing. We can multiplex the direction of communication. You have on the left-hand side a mobile phone, on the right-hand side a base station, and we have the so-called uplink. The uplink is from the mobile phone to the base station, and we have the downlink. Downlink from the base station to the mobile phone. And you see, we apply frequency division multiplexing for the uplink and downlink, so we separate direction using different frequencies. This is then called frequency division duplex, FDD. So FDD means you separate the direction, duplex, so we send and receive at the same time. We separate the directions by frequencies. We can do the same using different time slots, but here, that's what GSM does. We have an uplink and a downlink. Additionally, we can separate different channels using different frequencies. That is what you see here, the different channels, 124 channels. The channel width is 200 kilohertz. Then we have 124 channels in the downlink and 124 channels in the uplink. So you separate channels using different frequencies. And now who's assigning the channels? Well, with a mixture of different algorithms. So for example, the Bundesnetzagentur says, okay, the lower 62 whatever channels, that's for T-Mobile. And the upper channels, that's for Vodafone. So the algorithm in the Bundesnetzagentur splits those channels into two parts, one for T-Mobile and one for Vodafone. That's the example of the 900 megahertz bands. Within the 60-something channels, then T-Mobile decides. Yeah?
Can several mobile phones talk on the same channel?
Yes. Yes. So as we will learn, when we look inside a channel, GSM applies additionally time division multiplexing to basically split the channel when it comes to time into tiny time slots. Many time slots, and all creating a frame, as we will learn. And this frame consists of 8 time slots, and then a mobile phone is assigned a certain channel, that means a certain frequency, plus a certain time slot within the channel. This means you can support, in this simple example, in GSM, 8 participants, 8 conversations on one channel. But first of all, the Bundesnetzagentur separates the spectrum and says this is Vodafone, this is T-Mobile. Then T-Mobile has to decide, we use these 5 channels for this base station, this 8 channels for that base station, and has to do the frequency planning because we cannot have overlapping channels. This would cause interference. So first Bundesnetzagentur, separation, then in this example Vodafone, whatever, does the cell planning. And then within the cell, let's assume we have 3, 4, 5 channels, then the cell has to decide, well, I assign this time slot plus channel to this conversation and this to that. This is what we learn when we look into the GSM standard. This is where you see, okay, we apply FDD for the duplex, plus we apply FDMA for the channels. Plus, as you will learn, TDMA inside the channel. You can mix these different schemes. This depends on the standards. Yeah?
About the time division multiplexing, the station knows how it wants to decide the time slot, but how do the cell phones know that want to connect to the base station? Do they send all the time? Do they duplicate their messages so it's something?
Yeah. So, interesting question. How do the mobile phones actually know about the cell structure, the frequencies, the time slots? I will come back in more detail to this question when we cover GSM. Basically, it's in a way that initially the mobile phone listens to well-known, frequencies. So the mobile phone basically has to scan all the channels. If you don't know where you are, let's assume you don't know anything. Then you scan the channels, and then you will receive, there's a certain broadcast control channel, a broadcast channel, that simply sends out broadcasts. This is the network of T-Mobile, and you're here in Germany, and this is, you have a country code, color code, etc. So there's a certain code that tells you you're in this country, this is the base station, this is the network, and then you basically tell the mobile phone, and these are the channels you're allowed to use. Because there are frequencies they're not allowed to use in some of the countries. So for example, we do not have GSM at 850 megahertz in Germany, but in the US. The US doesn't have the GSM on 900 megahertz, etc., etc. So there are some restrictions, but the mobile phones, they're able to receive way more channels than they can use in a country. So they will receive the channel, and then they will initially also get some synchronization, because in the beginning they don't know where they are, they don't know any synchronization. I will explain this. Then they get some initial synchronization to frames, in the end to single bits. And if they are synchronized, they can start receiving data. Because if you're not synchronized, it's very difficult to receive anything. So you're synchronized, and that's it. The next step is, this is also what I will explain in more detail, when you want to place a call. Then, well, there's some competition for the resources. Your mobile phone cannot simply use a channel. That's what a wireless LAN does. A wireless LAN simply says, oh, here's the SSID, channel 12, great. I want to send something, send. Not mobile phones. They have to compete for the channel, and they have to send something like a request. That's a so-called random access channel. That's what I will explain then when I come to mobile phones in more details. They have to compete, and now the answer to your question, if they are successful, the base station will tell the mobile phone, This is the channel for data transfer, and this is your time slot, or these are your time slots. So yes, it takes a while. And if something fails, it's most likely, if you have a crowded situation, you will not be successful to get a channel. So there's some competition. But as soon as you have a assigned time slot, you can be sure you will have this time slot in the cell. Handover, etc., different topics, I will cover this later on. But good questions, how do you know? So several steps before the mobile phone actually knows the structure. So initially the mobile phone only knows I have a quad band receiver. I'm able to receive GSM at 850, 900, 1800 and 1900 megahertz. That's it. And then you have to search. This is also why it takes a while before the mobile phone is, well, actually registered in the system if you arrive in the US, for example. Because the mobile phone remembers, oh, when you, okay, switched on, I was with this network in this country, then I try these channels first. Then it's much faster. But if you're in another country, it takes some time. You have to scan the channels. You don't know it.
Maybe this is the detail, but how are the time slots defined? I mean, probably it's not the date and time and seconds, because then the clocks would have to be synchronized. So how are the time slots defined? I
will explain. So the question is how the time slots are defined. Well, the standard clearly says I have a time frame of in GSM 8 time slots. The frame itself is 4.165 milliseconds long. That means 477 microseconds per time slot, something like this. And within the time slots, the standard says exactly how the bit patterns look like. I will explain what happens if you're not precisely synchronized, and how does it work with the gauge spaces and the distance to the base station, etc. Next chapter. So next chapter I will explain exactly this. How are you synchronized? How do you actually synchronize your time slot? Because you can imagine, you move towards a base station, away from a base station. This actually shifts your bits somehow within the time slot, and then you run out of sync. How is this handled? Wireless LAN doesn't know all this, because you're very close to the base station, and you're not moving at 200 kilometers an hour, or 250 or whatever. So with the train, etc., etc. So this is what we will cover in chapter 4. So wait for the next chapter and then some more details on this. So here, first of all, we separate our frequency, our spectrum. Something similar we can do in time. Now this is a combination of TDD and TDMA, but be aware, you can also combine TDD with FDMA and FDD with TDMA, or TDD with CDMA, or whatever. These are just examples how this is used. TDD, that means, you see, downlink and uplink separated in time. So they're separated in time. So first downlink, then uplink. First downlink, then uplink. First downlink, then uplink. Additionally, you separate the uses using time slots, 417 microseconds, 12 time slots for the downlink, 12 time slots for the uplink. Or this can be also asymmetric. So more time slots for downlink, fewer time slots for the uplink. Might be a good idea. So that is more flexible. If you think back, the FDD scheme in GSM had the same amount of channels for the downlink as we have for the uplink. This was symmetric. Can you imagine applications where symmetric is a good idea? Or can you imagine applications where asymmetric is a good idea? What is good for symmetric? Uplink and downlink. Yeah?
Maybe talking on the phone.
Exactly. Voice, talking on the phone. Voice communication. Because we know, we learned the telematics, 40% one sender, 40% the other sender, and remaining 20% silence. Thinking. The other one said this. Think, answering. So that's rough numbers, but 40, 40, 20. It's symmetric. And asymmetric, surfing on the internet. Huge download, little bit of upload. Well, it's a TCP or HTTP request, TCP SYN, whatever. And then the file comes down. So you see that depending on these, in this case, FDD, TDD scheme, a technology is better or not so good suited to certain applications. But all the designers had voice communication in mind when designing GSM, also the initial UMTS. Today it's a little bit different. So here we see TDD for time division duplex, so separation of the directions, and TDMA, within one direction we can separate different users, different channels. That's used in DECT, the standard for cordless telephones. So if you have a cordless telephone at home, most likely it's following the DECT standard, so a digital cordless telephone standard. Okay, that's also one way of separating. And the clever algorithm now is, well, the engineers decided uplink, downlink, but then the internal algorithm of the base station of DECT has to assign time slots to users. So that's the idea. Okay, DECT. But then these are pretty fixed schemes. There was something very flexible. Yes, in telematics we had ALOA. Why can't we use ALOA? Remember what was ALOA? So the pure ALOA simply says, okay, it's a random mechanism where we have 3 senders, and if they want to send, they simply send. We have no central arbiter. It's a time multiplexing scheme, and where does it come from? Remember Hawaii mountain base station, and we have senders on one side and on the other side. They do not see each other, hidden terminals. So without any further synchronization, and if you want to support spontaneous traffic, you just allow them, okay, send whenever you want. The collision will happen here. Similar scenario if you have a satellite and ground stations. We could think of a kind of a polling scheme. Yes, polling works, but polling usually has a higher delay because you have to wait. You have to wait a little bit because, okay, polling, nothing there, nothing there, nothing there. Oh, data to send. So if you do a round robin polling, for example. So if you do ALOA, you can spontaneously simply transmit your data, and we know we might have collisions. And the collisions, they will happen at the receiver. And the senders will not notice anything from the collisions. We need additional mechanisms outside of the classical ALOA to notice the collisions. For example, we say we have to have an acknowledgement. But that's a different layer. The collisions happen on the physical layer, and there's no way of performing collision detection. But we can replace this by saying, okay, we have to have an acknowledgement. As soon as we have successfully received data, we have to send back an acknowledgement. That's, for example, implemented in the wireless LAN standards. So if you transmit a unicast packet, you will get back immediately an acknowledgement. If not, you know, oh, something happened at the receiver, but you will not hear the collision. So you cannot apply the CD. We're also aware of slotted ALOA, so that's a slight improvement. If you say, okay, at least we have some time synchronization, that means our central base station will basically send a kind of a clock, or at least whatever, some kind of a synchronization signal. So then it depends of the traffic characteristics, how many collisions we have, how much data you actually destroy using the collisions. We had this in telematics, depending on the traffic distribution, etc., etc. What is the efficiency of these schemes? So yes, if you know nothing about the setting, that's all you can do. And by the way, slotted ALOA is the best you can do if you have an uncoordinated medium access. Uncoordinated means you do not apply any additional algorithms like polling schemes, like a master that synchronizes somehow and applies some time division multiple access. So if you're completely new as a mobile phone and you don't know anything, and at least you're time synchronized, your initial step to get additional resources like time slots is exactly based on slotted ALOA. So you will find slotted ALOA schemes in GSM, in UMTS, for example, for the initial medium access. So you dial a number, you don't need a medium. As soon as you push the green button or whatever it is, then the mobile phone will apply for resources. But this initial applying for resources might cause some collisions. You contend for the resources. So this is exactly where you use a slotted ALOA scheme on the so-called random access channel. So that's when we come to mobile phone system. So that's one of the channels, random access channel. That's exactly where you have these schemes where, well, a little bit more elaborated, but basically these are slotted ALOA schemes because you're already time synced with the base station, but you don't know, you're not aware of any time slots. So you apply for the channel. So you compete for this, and then the base station assigns resources to you. But at New Year's Eve, for example, Brandenburg Gate, if you're not able to place a phone call, well, then it could be one of the reasons might be that you're not successful with your initial random access. To start setting up a layer 2 connection, then via this you will get some resources. And then you can start the phone call, etc., etc. So there are some more steps needed, as I will explain. So random access channel, that's one of the reasons. Even for emergency calls, have to use these random access channels. So, okay, that's one of the problems you have if there's enough capacity on these channels. So, ALOA. Then there are some more, maybe some more efficient mechanisms for wireless, wireless settings. So we learned in telematics that depending on the distribution, etc., with a certain efficiency for ALOA, slot ALOA, which might be not a good idea for the real data transmission. But basically that's all you can do if you do not know anything about the network. So one idea is that we actually introduce two phases. One phase is kind of a contention. Contention using ALOA or maybe slotted ALOA. A short contention. And then followed by, sooner or later, a second phase where you really have the data transmission. Hopefully without any collisions. So, one idea in wireless schemes is short reservation phase, longer data transmission phase. So that's one of the ideas. So you can show that depending on the setting, the reservation of the medium can increase the efficiency. But yes, this is not spontaneous communication anymore, because first you have to make a reservation, then you have to wait before you say, okay, access granted, and then you can access the medium. Yes, so you cause higher delays. We will learn that also wireless LANs know exactly also this mode. They know a spontaneous mode, and they know a mode with first reservation, then data transmission. And this is what the wireless LANs can apply if the noise level increases. Increased noise, increased interference means, oh, many others try to send something, then maybe it's a good idea to have first a reservation and then a data transmission. And the basic idea is that the reservation phase is very short and does not destroy the data transmission, which should be longer. So, very short reservation, longer data transmission. So, that's the idea. And there are different schemes. I will explain some of them, not all of them. You can look into the slides. There are many of these schemes, but the basic idea is always the same. First reservation, then data transmission. And that's what we learned from satellite links 60s, 70s. So these are the classical settings. So one thing is that you have this explicit reservation, sometimes also called reservation ALOA. So that has exactly these two modes. That's the phase one, that you say, okay, I try to reserve a time slot. You can imagine, now let's go for this situation. We have a satellite somewhere up there, a satellite with a satellite dish, and you have the ground station somewhere here and somewhere there. And they try to get some resources to transmit something somewhere, doesn't matter. So first what they do is they do exactly this reservation. So they compete, And then, so that's the first step, they compete for time slots. So for example, the yellow ground station tries to get this time slot. If successful, this time slot is then reserved in the second phase, the data transmission. In between, the satellite has to send to all ground station a kind of a reservation map, so that you can see, oh, my request was successful or not. Because it could be the case that we have collisions. The ground stations are not synchronized. Because if we had a cable between the ground stations, why using the satellite? So, at least for the broadband communication. So that was the original idea. So, first, competition using ALOA, slotted ALOA, for example, they can be synchronized because the satellite synchronizes them. So slotted ALOA, a competition, and then the satellite will tell them, send basically a reservation map, some kind of a map, reservation map that tells all the ground station, okay, now slot 1 is for this ground station, slot 2 for this, slot 3 collision, slot 4 for this. So if we have a collision, okay, tough luck, that's it. So there's a certain reservation list or map, and this has to be consistent. So they are all synchronized, that's the idea, but that's simple, because they all see the satellite, but they do not see each other. That's the setting. And now you can transfer exactly this scheme to our wireless, whatever network setting. Now we don't have a satellite, but a base station, and we have many mobile devices. It's basically the same. So the idea is that, yes, we still have collisions, but with a very short ALOA phase compared to a long data transmission phase. So what do we do with the slots with collisions? We could try to transmit something. No guarantees, guarantees only for the reserved slots, but if we have slots with collisions, so maybe here we have a collision, we see in this map that there's a collision, we can actually, based on some random function, still transmit something. Maybe not that important things. Maybe wait for an acknowledgement. So we could still reuse this. So we can explicitly reserve something. There are also some implicit reservation mechanisms that we can say, okay, we have certain frames. Now in this example, 8 time slots. And all, again, our ground stations, for example, they are synchronized. Okay, what do we do now? The satellite always sends on the downlink from satellite to Earth a reservation list. A list that tells all the ground stations, slot 1 reserved by A, slot 2 reserved by C, etc., etc., slot 6 reserved by A, slot 7 free, slot 8 reserved by F. Just an example. Why is this implicit? Well, you do not have to compete again and again for each of these 8 slot frames, but if you have a reservation, then it's quite clear that you can keep the reservation as long as you want in this example. Like A. A keeps slot 1 all the time. That's nice for TV transmission over satellites, for example. Okay. If you stop using your slot, like for example D, maybe D had slot 3 all the time, then after stopping, so D doesn't send anything here in this, slot 3 is empty, the satellite will recognize this and then send on the downlink, slot 3 is empty. So you don't use the slot, satellite notices, slot 3 is empty, and then for the next frame, for example, the stations can compete. Maybe some station, whatever, X and Y, compete for this empty slot. And then we could have a collision. It's a reservation at 10. We can have a collision. How do we notice that there's a collision? Well, very simple. In the next reservation list on the downlink, we still see the slot is empty. Oh, okay. This is how we notice that we have a collision. Okay, then the slot is empty, no one is allowed to send, but again we can compete, and now E was successful, and this is signaled to all the ground stations. So that's the idea here. So we have some kind of an implicit reservation. If you're successful, you can keep your slot. If not, you will notice it during this downlink time when the satellite sends you this short list. And always think of, you want to transmit a lot of data, factor 1,000, 10,000 more compared to these short lists or compared to this reservation phase. Then it's worth doing this two-phase schemes. So these are all schemes, as I said, from satellite era, late 60s, 70s, but you can apply these or similar schemes also for any other wireless networks. I will come to concrete technologies when we'll discuss wireless LANs and GSM and UMTS and LTE, how this is done there. Okay, and then there are some more, refinements, enhancements, etc., defining mini slots and reuse of free slots, etc. You can look into it. It's not that important. So, one example also for these two phases is not only DMA, etc., these reservation schemes, but one scheme used for wireless LANs. Wireless LANs, well, we know detection, so a D here does not really work. So this is why we quite often say, okay, we have a kind of a carrier sensing, as we will learn, scheme in wireless LANs with collision avoidance. Not really detection, but avoidance. So we try to avoid. So what you can do is, that's phase number 1, you can send, as I will show, first some packets that reserve the medium. So first this reservation phase, and then we go into phase 2 and transmit data. And within this reservation phase, we transmit sender address, receiver address, and packet size. Why? I will explain in the next slide with the help of a figure. So first, let's say phase number 1, we try to reserve the medium. Which problem do we solve? We had hidden and exposed terminals. The problem was that A and C, for the hidden terminal problem, they send, and we have the collision at B. Now we first have phase number 1, the reservation. Why? Now again, A and C both want to send something to B. First, what they have to do is they have to send an RTS, a request to send. Okay, now what can happen? So if both send their RTS at more or less the same time, these are very short packets, so the probability for collision is much, much lower compared to the long data packets, but it can happen. Then we have a collision of the RTS. Then station B will never answer. Okay, collision, let's try it again. But if one of the stations is successful with an RTS, then B, if it can receive something, immediately sends back a CTS, a clear to send. And now, and this is the trick, this clear to send will be heard by C. Because, as you notice here from this red transmission range, C is within the transmission range of B. But the CTS contains sender, receiver, packet size, as I just said. So it contains A wants to send to B for a certain amount of time. And this signals to C, oh, I don't know A, but I know B. I want to send something to B. Oh, some A sends something to B, and I receive the clear to send. That means if I now start sending, I will destroy the data packet sent by some A. I don't know, but there's a station A. And then C has to wait for a certain time. Well, how long? At least for the length of the packet. Because it takes some time to transmit the data packet. Because after this reservation phase, if A receives the CTS, A will start sending its data packet for a certain amount of time. So this medium access with collision avoidance is an optional medium access method for wireless LANs. If they experience too much interference, you can switch this on. And quite often in the drivers you see this as an option. You can switch this on or automatically or whatever. So that's one way of handling these hidden terminals. And now you don't have the problem of hidden terminals anymore if, that's just a remark, if you assume more or less symmetric connections and you assume not two mobile terminals. Because it could happen that after someone sends the CTS, you move into the transmission range, you never heard the CTS and start sending. Yes, this can happen. Or you have very asymmetric communication scenario. This depends on the antenna characteristic, for example. So it might be the case that it's very simple to send from A to B, but it's difficult to send from B to A. So an asymmetric situation. This depends on antenna shape, on the surrounding, on the low noise amplifier, on the whatever output power, on many scenarios. So here we assume more or less symmetric links. And yet another remark, in real life, well, we have a huge test bed here, and we experience sometimes 70% of the links are asymmetric. Up to more than half are unidirectional links. Then all these schemes fail. So that's not 100% guarantee that it works. It's an improvement, but not a guarantee. In wireless systems, you never have guarantees, never. So, okay. We had another problem, the exposed terminals. That was the situation. B wants to send something to A, and C wants to send something to some, whatever D, we don't care. So, exposed means C has to wait, because the medium is busy. Busy because B is sending something to A. But now with the help of Macra, B sends the RTS. That means A and C receive the RTS. They read, okay, B wants to send something to A. I'm C, I'm not A. Okay, so let's wait. I never received the CTS. You see, this CTS will never reach C, the CTS, because I'm outside of the transmission range. You see this blue? Oh, sorry. The signal will never reach me here. So that means for C, yes, I got the RTS. B wants to send something to A, but I never heard anything of A. So A, assuming symmetric links, A is outside of my transmission range, so I can easily start communication with a station D without interfering. That's the hope. With the communication between B and A. So we don't have to wait. So we solve the problems of exposed terminals. It's a certain probability. So you see, that is one of the schemes, an optional scheme for wireless LANs. All wireless LAN stations have to follow these rules, but they don't have to use it. But if one of the stations use the rules, they all have to know how to handle it. Waiting times, etc., as we will learn in chapter 7 about wireless LANs. Okay, so that's one way of handling hidden and exposed terminals. Then, just to make the picture a little bit more complete, sure, you can use polling mechanisms. Polling, that's what classical USB does. You can simply poll terminals. So that's the classical 60s mainframe terminal scenario. You can just ask terms, you have something to send, something to send, something to send. Well, this sounds, well, very traditional, but that's exactly what, for example, Bluetooth applies. Bluetooth, as we will learn, you have a Bluetooth master, and you have up to 7 slaves, and the master polls the slaves, if the slaves have to send something. If not, okay, poll the next slave, etc. So that's the classical Bluetooth. So there are many, and you can look this up in the literature, many different schemes how you can perform polling. Okay. Then there are some special schemes you don't have to learn all these schemes, just to show you, okay, there are many different ways how you can solve the problem, that you send a certain signal to the stations, and as soon as you receive this certain signal, you notice the medium is busy. The problem still is hidden terminals. Those two terminals, they will not see each other, but the base station sees, oh, there's one terminal sending something to me. This is why I send a busy tone to all the others. As soon as I stop sending a busy tone, the stations can compete. That's another idea. So you see, over time, the engineers had many different ideas of solving this issue of hidden exposed terminals in the wireless access. So, but that's the main topic. Now, these are schemes: frequency, time, space, more or less easy to understand, I say. The problem is this code division. Code division. I always said, okay, I will shift this to this lecture. So, code division, how does it work? I told you, same frequency. So, UMTS, for example, UMTS, we have a 5 megahertz channel. So, 5 megahertz. All the users of Vodafone using UMTS use the same 5 megahertz channel all over Germany. Okay. Probably at the same time, we don't know. We don't know when you place your call, we don't know. And you can use the whole bandwidth, more or less, for your transmission. Okay. The trick now is you use spreading. That's exactly this XOR, but not spreading with a fixed scheme, but spreading with a random number. And if you do not tell anyone this random number, then you cannot receive the signal. Okay, how can you explain this? And the classical example, how you explain CDMA, is the so-called party example you will find in all textbooks. Party example simply means that you're at midnight at a party, 30, 40 people, and have conversation all over the place. International party, so you have guests from Finland, from Sweden, from Germany, from Austria, from Switzerland, but also from Kenya, whatever. And they all talk to each other, and in this case they don't all use English, but people from Finland, they use Finnish, Swedish, German, whatever, Swahili, Chinese, Mandarin, Cantonese, whatever. And now what does code multiplexing mean? If you do not know the code, you will not understand anything. So if someone tells you Mina Rakastan Sinua, for example, who understood this? Iksi kaksi kolme? You cannot even count to 3 in Finnish. Oh, I'm disappointed. No. But if someone says 1, 2, 3, you might understand. 1, 2, 3, close. You will understand. Why? Maybe you learned some French, so you will understand some Spanish, some Italian. If you know German, you will understand maybe a little bit of Swedish, but Finnish? Mele vatele? Important sentences. That means, do we go to my place or to your place? These things, or the first one was I love you, so you should understand some Finnish, but this sounds like, okay, that's different. If you don't know the code, you don't understand anything. And that's exactly the idea of code multiplexing. So, you apply a certain code. If you don't know it, you will not receive it. And the codes have to have certain characteristics. We learn the codes have to be orthogonal. Orthogonal, math, remember, basic lectures, what does it mean? 2 vectors orthogonal, inner product equals 0. If the inner product of 2 vectors equals 0, 2 vectors are orthogonal. N-dimensional vector space, remember, orthogonal. Here, this is computer science, so if the inner product is more or less 0, close to 0, we say it's almost orthogonal. And now it depends on how orthogonal your code is, if you can separate different conversations. What happens in the parties? You will notice that if 2 people from Finland talk to each other, it's no problem to use same frequency, in this case acoustic waves, at the same time, same room, and you can start a conversation in German. Yes, and you will receive the Finnish language as background noise and vice versa. But as soon as you know the language, you know the code, This is not background noise anymore. So if someone from Austria, if two people from Austria talk to each other, see those codes, they are not that orthogonal. You will understand from time to time, depending on where they come from. You will understand more or less. Or if I start talking my dialect, you will understand most of it. Maybe not all the words. But so my dialect is not really orthogonal to, that's what we usually use in Germany. So you will understand most of it. And so that's exactly the idea of code multiplexing, using a more or less orthogonal code. And then what others basically say in those languages, it's background noise. But what you also will notice, the late in the evening, etc., you start talking louder, 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 louder. So the background noise level increases and suddenly your communication breaks. So although the code is orthogonal, if people from Finland, in the evening they are louder and louder, or those from Germany or whatever, it doesn't matter. The noise level is too high. So your signal to noise ratio is not good enough anymore. So you can increase your output power, but there's a certain limit, depending on your voice. Okay, conversation breaks. And this is why it's so important for these code multiplexing technologies to have precise power control. So that you lower the output power to a certain minimum, that conversation is still possible, but you do not create too much background noise. So you will not be able to listen to the conversation as long as you do not know the language, which means the code, but it contributes to the background noise. So that's the basic idea of code division multiplexers. So you create a code, and how you do it? Well, basically you pick a random seed, you feed this in a random number generator, and then you generate random numbers. You use these random numbers for spreading your original data. So all you have to know is basically the seed for your random number generator. The generator itself, it's fixed, it's in the standard, that's hardware. But you need the seed and you need the phase. So where are you? Well, you generate many, many random numbers, so where are you? You know the seed, you know how you generate the random numbers, so where are you now? So that's important. And then you can synchronize and receive something. So that's very roughly the idea of CDMA. So you can tune into the signal if you know the pseudo-random number. And how? I will give you some examples. Yes, it's a little bit more complex. You have to take care that you have more or less the same strength. This is why we have this quite strict power control, 1500 times per second. Way more than normal GSM or wireless LANs. And this higher complexity results in, well, less battery lifetime. If you compare the lifetime of a classical GSM system with a UMTS system, you will see, oh, you drain your battery much faster. Nowadays, together with the smartphone functions, etc., you have to recharge every day. Classical GSM phone every 2 weeks or every week, so with much less capacity of the battery, but that's due to all the other things you do on your smartphone, besides, well, from time to time using it as a phone. Okay, yes, there are some disadvantages, but also many advantages, like you don't need this frequency planning. You have a huge code space compared to frequency space. You can easily generate many orthogonal codes. Yeah?
How do you tell this random number just generated with the person you communicate with? So
the question is, how do you actually tell the random number? Well, again, the very basic idea, more when we come to UMTS, is that there are common channels all the phones can use with the base station, and then the base station can assign the phones a certain random number. So basically you start with a well-known channel, a channel where you do not have any coding. So that means, for example, in our example, that everyone knows English, and then you tell the other person in English, from now on we will use Swahili. And then both switch to Swahili, and then they communicate. That's the idea.
if you tell it in English, then everybody will know.
Yes, exactly. So that's not, yes. So the question is, if you do it in English, everyone will know it. Indeed. So this way of distributing this random code is not a way of encrypting or for keeping your conversation secret. There you have to apply additional mechanisms. For military use, for example, you can think of, and this really exists, you can think of coding the secret code into your devices, not during manufacturing, but when you apply them. For example, if you have artillery and you have grenades, when you fire your grenade, you can code the secret code into the intelligent grenade, and then you can communicate with it using the secret code. That's one way. Or code it into whatever device. So there are interesting ways of using this. But if you want to use this for keeping the communication secret, then indeed you cannot use a broadcast channel. Then first you have to do this classical public key infrastructure, key exchange, etc. mechanisms. I will explain this in a simplified version when we come to GSM. But you're right, if you tell the code, then it's not secret anymore. Yes, that's true. But here, usually for civil systems, it's used to separate the users. So, as we learned, when we look into spreading, interference is not coded, and you can easily integrate encryption. You can, if you want, if you do not tell anyone the code, yes. And also there are nice ways of implementing forward error correction depending on the spreading factor and how you do the spreading. I will give a simple example that you see how this works in theory. I'm aware that this is not 100% the reality, but as I told you, there are nice, interesting books about CDMA technology. We cannot cover all the details here. So, very simplified in theory, that you understand. Okay, party example, keep this in mind. But now, let's go back to ones and zeros. We have a sender A. The sender A wants to transmit, in our case, a single bit. That's our bit A. AD, data, 1 bit, a 1. And we have a simple key. In our case, the key is 010011. So, we have a spreading factor of 6. Now, to make math a little bit simpler, as I told you, that's computer science, we simply say, okay, let's assign the digital 0, or data, let's assign the -1, and the logical 1, or digital 1, let's assign the +1. It's just simpler for the math. Now what do? We send the signal. So we basically, this is exactly our spreading here. That's the spreading. So we multiply our 1 with this key. So 1 times -1, because the key is a 0 as the first chip. We learned these are our chips. Results in -1, etc. So that's the result if we spread our initial data. So we want to transmit, sender A wants to transmit a logical 1, applies the key. In real systems, we have spreading factors of 2, 3, 500, up to 10,000. Okay, or sometimes only 2, it depends. So now B also wants to send something. B wants to send a 0. Okay, uses a different key. The key of B is different from the key of A. Now, the resulting signal, you see here. Apply exactly the same. Now what happens in the air? Simplification, simplification. We simply overlap those two signals. I know, in reality, they are not synchronized, they do not perfectly overlap, plus there is noise, etc., etc. But in our very simple scenario, let's assume they overlap. So the resulting signals superimposed, we neglect many things. It's just for the basic principle is as follows. Well, we have this value of -1, if you think in signals. Now, two values now -2. We overlap. But we also have the case that parts of the signal, they cancel out each other. -1 and +1. Cancel out. Oh, that's tough luck. You see, this results in this, we don't receive anything. That's now, assuming these simplifications, our superimposed signal. Because they don't know of each other, they both send same frequency at the same time. So what do we do on the receiver side? And now this is this magic. We apply the key. So mathematically, we create the inner product. So, on the receiver side, we know the key, we know the superimposed signal, that's what we receive, and we apply the key chip-wise. That assumes we are synchronized. Yes, synchronization is quite important. I will explain when we come to UMTS and GSM how we perform the synchronization. But now let's assume they are synchronized. So we apply the key, so -2. And the key up there, you see the key AK is from up there. This key, if we apply it, the key is, if we translate it into this -1 +1, it's -1 +1 -1 -1 +1 +1. That's the key from up there. Okay, now we apply this chip by chip. So -2 times -1 results in 2. 0 times whatever is 0. 0 is 0. -2 times -1 is +2. +2 here +2 times 1 is +2. 0 is 0. So the result is then added. We create the sum during a bit time. We still want to transmit the single bit. So we create the sum over this bit time. In real systems, we integrate over time. But here, I showed this as a discrete example. We sum this up, and the result is 6. Oh, what does it mean? And now, the definition is, in this example, if the result is greater than 0, the original bit was a 1. If it's less than 0, the original bit was a 0. Now you can play with arbitrary bit sequences, here only shown for a single bit. You can do this at home, apply this as often you want. You will always either get clear a 6, which means a 1, or a -6, which means a 0. Why do we have a clear 6 and a clear -6? Because in this case, we have no noise, we are perfectly synchronized. So in real systems, it looks a little bit different. But this is exactly the basic theory of CDMA. So we apply the key, and if we do not know the key, there will be a result, but maybe a wrong result, and we'll notice this when we then apply the checksum, for example, on layer 2. So that's the basic idea of the CDMA. So if we look now in signals, we can still simplify it. If we transmit now 3 bits, this is our 3 bits, and we apply a complete key sequence. This is all idealized, you know, those signals, they do not exist, etc., etc. And we know we use longer spreading factors. Still, we have a spreading factor of 6 here. You see, 1 bit spread by 6 chips. But now in this case, we do not apply the same key for each bit. That's one way of doing it. But usually, we generate a pseudo-random key sequence with a pseudo-random generator. We do not have real random generators in our normal computers. So, all pseudo-random generators. And so we generate the key sequence, we apply this to the data bit, then we generate our spread signal. That's a spread signal from A. So we spread it over time. And then we do the same for B, and we also have then the signal of B. So that was A, and that is B. And this is superimposed when we transmit it over the air. So that's just to make the idea of CDMA a little bit clearer. These are just examples. So we superimpose them, and as you see, okay, low level, even lower level. Low level, and high level, they cancel out each other. So if you look at this signal and this signal, so we have high and low, if they two come together, they cancel out each other. So that's what happens in space. If two electromagnetic waves, they interfere, well, they can cancel out each other, like acoustic signals. So that's the resulting signal. And now we apply exactly what I said. We create the inner product. So we create the sum over these chips. But, so now this was our superimposed signal. That is what we have over the air. And now what we do is we apply our key. So that's the key. Well, here just shown as signal, but that's our key. We know the key. We have to be synchronized, etc. We simply apply this. We multiply. We create the inner product. And the inner product you can create chipwise, or you can basically now, for this example, look at the signal. What happens if we multiply this? So in this case, negative times this positive creates a negative signal. If the signal is 0, that's the 0 line here, 0, then the result is also signal 0, etc., etc. And so you create this signal. What does it mean? If you now think in hardware, you can create different voltage levels, for example. Negative voltage, 0, and positive voltage. What you can do now is you can charge a capacitor. A capacitor, this element, you can charge and discharge it. And at the end of the bit period, you can check what is the charge of the capacitor. Is it positive or is it negative? A capacitor is nothing but you integrate over time. So you integrate, you get different voltage level, you sum up, but you know summing, and then if you do this very, very, very often, and then at the end you end up with the integral, etc., etc. So you integrate over time. So basically you charge a capacitor, just another way of explaining it, and at the end of your bit duration, that's a real data bit duration, you decide, am I negative or positive? And then depending on your definitions, this either means I transmitted a 0 or a 1. In this example, if you are negative at your capacitor, it means you transmitted a 1, positive it means a 0. That's just definition. So you can think of, okay, you can implement this also using real hardware. Again, simplified, but you can think of, okay, that's what you do. So you integrate over a complete duration of a bit, of a data bit. You receive this many chips, well, your signal, you multiply this with your key. This results in a certain, let's say, voltage level. You charge or discharge a capacitor, and then you check at the end, what is the voltage? Or you can do this fully digital, as I showed you in the example before. It's just ways of making this a little bit clearer, that you have a basic understanding of this technology. If you are further interested, look into the same you can do on a signal level for B. Also you get these nice outputs, but what happens if you do not have the key? And that's the example here. Again, we have the superimposed signal, and you have a wrong key. Again, you can calculate this inner product. You can feed, simplified example, a capacitor. You can charge, discharge it. And so this is our integrator, so technical implementation of integration. And then the output, well, you see your negative, 0, positive, positive voltage, 0, positive. So in the end, you're slightly negative, and then you end out positive. Positive in our definition was, for example, a 0. So there will be some output all the time. Here we have a problem. If the capacitor signals, okay, I integrate over time, the result is 0. Okay, we have a problem. But who will catch now these errors? Because these integrators, they will always come out with a result. Usually this creates bit errors. So you have your bit error, And the problem is, sooner or later you try to correct it, but then you will also calculate your CRC. And this usually is then the point where you say, oh, it fails, you cannot receive it. So you cannot create meaningful data out of this garbage if you do not have the key. So that is a kind of a simplified explanation how what it means to have the right key or to have an arbitrary wrong key. Now it depends on the length of the key and the way you generate the key, how good the key is. And this is where you also can have your own lectures about how you generate good keys for CDMA technology. So that's one of the key questions. How do those keys look like? There are certain gold codes and this and that and whatever. This is what you can look up in literature. How you create this, what are the characteristics of these keys, what does it mean orthogonal, what is the problem if you introduce noise, what is the problem if you're not time synced really, all these things. But that is a very basic idea of CDMA. And what you should have understood is that, okay, we create certain codes. The codes have to have certain characteristics, be more or less orthogonal, remember, different languages, and that's how we can separate the different data streams. And all the details are left for, I would say, more electrical engineering or further study if you're interested in this. This technology is not that easy to handle. In the very beginning of CDMA, there was a really fierce battle between mostly US and Europe about which technology is better. And many people in the US said, well, CDMA has a much higher capacity, much higher. And this was one reason for not introducing GSM in the very early years. Because GSM uses TDMA, FDMA and TDMA, much simpler as a scheme. But many said, no, CDMA is much better, and the company Qualcomm had the chips, the technologies, the patents, etc. And then CDMA was also pushed through as a technology in UMTS. Today, many people say CDMA is good for academia and PhD thesis, but FDMA and TDMA is in the end easier to handle, and we will see how the fourth generation of mobile phone systems went back to TDMA and FDMA. No more CDMA. Because as you can maybe guess from this explanation already, this might be a little bit more complicated to handle. Yes, it's nice to use same frequency, same time, that's nice, but it's not that easy to handle. Okay, so there are some more interesting things that you can use CDMA without really code division, using always the same code and just using the not synchronized senders, etc. That's, by the way, by Norm Alperson, the inventor of Aloha. He had these ideas, etc. Interesting. So in the end, if we compare the different technologies, they usually do not come alone. There is no system that applies only FDMA of the today modern systems. Usually you have a combination. So, for example, if you go for the GSM system, as we will learn, it uses, well, time, frequency, and also space. Place the antennas a little bit further away. If you use UMTS, yes, the Bundesnetzagentur separates different operators by frequencies, and the single devices, they use a lot of CDMA. They use some TDMA for control traffic, etc., etc. So usually technologies use different schemes at the same time. A wireless LAN uses also some FDMA, different channels, TDMA also to separate different transmissions, SDMA, you space them a little bit apart, the different hotspots. So this table just summarizes the key characteristics, the idea, and what the terminals have to do, how you separate the signals, and this is what you should know, basically, this summarized table, some of the advantages, some of the disadvantages, and usually, as we see, usually we combine the technologies. And also some of the technologies, they have some more complexity. We had many expectations in the early 90s in CDMA. Today, well, yes, it's a technology that's used, but as we see when we look at LTE, for example, now we have better signal processors, so we can use FDMA and TDMA in a very, very flexible way. So we do not have to use the CDMA technology anymore. So they have all their pros and cons. So that's basically all chapter 2 and chapter 3, all I wanted to say about the very basics, signals, signal propagation, key characteristics of multiplexing and multiple access. We could talk many more hours about specific features, but there's not that much time. So I thought it's much more interesting to explain the real systems. So that's basically all I wanted to say to the more physical layer, to the lower layers, about some specific characteristics you should be aware of when we come to higher layers to understand the problems we have there. Like the problems we already touched, like, oh, how does a mobile phone know when a bit starts? What happens if I move closer or further away from a base station? Oh, okay, how does it work? So are there some more general questions left on the lower layers? Signals, multiplexing, and all these things before I start with the communication systems. Okay.